One of the two semi-plenary presentations today is given by George Pappas from the University of Pennsylvania, USA. The 70 minutes presentation is followed by an interesting live event. The session is chaired by John Ligeros from ETH Zurich, who will now introduce the speaker.
Good afternoon and welcome to this afternoon's semi-plenary. My name is John Ligeros and it's my great pleasure this afternoon to introduce my dear friend and colleague, Professor George Pappas. I'm sure many of you know George already, not only for his seminal research contributions in control theory, but also for his leadership qualities and the contributions he has made to our community over the years. Among many of these contributions, he has been a central figure in efforts over the recent years to define the position of electrical engineering in general, automatic control in particular, in the greater scientific landscape, and the role that control theory is called upon to play in today's world. George did his studies in the US, first at RPI and then at UC Berkeley, where he obtained his PhD, and then joined University of Pennsylvania, where he's currently serving as the UPS Foundation Professor and the Chair of the Department of Electrical and Systems Engineering. His research work is very extensive and branches out from control theory into other disciplines, for example, robotics and computer science, where he's been central in efforts to combine methods, for example, for formal methods and privacy with control engineering. So George creatively combines methods from all of these disciplines to solve pressing problems in timely and real-life, large-scale, complex systems. His work has been recognized by numerous awards. I won't go through the extensive list, but just to mention the prestigious Antonio Ruberti Young Researcher Prize, the George Axelby Outstanding Paper Award, and I believe twice, the Hugo Schuck Best Paper Award. And today he will tell us more about his recent work, his latest efforts in combining methods from control theory and in this time machine learning. And he will talk about autonomy with deep learning in the feedback loop. So it's a pleasure to introduce George Pappas.
Hello, everyone. I would like to thank the organizers for inviting me to this very special Ifac World Congress. And I would like to thank my friend John for the lovely introduction. What I would like to talk to you about today, which is aligned with the theme of the World Congress, has to do with safe autonomy, with perceptual uncertainty, which essentially means deep learning in the feedback loop. I'd like to also thank my students, my group, my postdocs that have, and alums that have really contributed, in fact, led the work, and as well as the numerous sponsors that have helped me and supported the work of the students for all these years. In particular, I'd like to highlight contributions from NSF, DARPA, AFOSR, and ONR for this particular work. So the vision that I'd like to have for autonomy in the future and autonomous systems in the future is autonomous systems where systems that used to be primarily in manufacturing and industrial lines. And I think now with the increase of intelligent systems, we're sending them out in the wild. And the kind of applications that we're envisioning are things like sending UAVs for surveillance or for monitoring or for mapping services, as well as, of course, there was a vision of Amazon Air Prime for autonomous air delivery. Of course, self-driving cars have captured the imagination of the world for the past decade, as well as environmental monitoring. And I think agriculture, the impact of autonomous system in agriculture is sort of an area that is going to grow over the next decade. So despite this vision, especially in the area of self-driving cars, I should say this is not a self-driving cars talk, but it is one of the motivating applications for the work we do. There has been a lot of things that have gone wrong over the past few years. And 5 years ago, we were promised driverless cars, in fact, in 2020. And 2020 has arrived, and There was an article in the Spectrum saying that essentially that, driverless cars are not here yet. And there are many reasons for this. I'm not going to elaborate through the many reasons, but I do think that there is a realization now there that this is a long road ahead, and there's a lot more research, fundamental research, technological advances that are needed in order to get there. So today I'm going to talk about some of them, and I would like to start by saying what have we done well and what are some of the challenges ahead. So what are some of the trends that I see? So there's no question that deep learning has revolutionized a few fields, in particular the area of computer vision perception. This allows us to perceive environments in ways that was not before possible with any prior technique. And that has actually led to a deep learning revolution in many other fields, including our own field of control, as I'll talk about a bit later. Despite these tremendous advances, the fact remains that even though deep learning may be very good for a variety of perception tasks, when it comes to safety critical applications, such as self-driving cars or medical imaging, it remains very fragile. And these are some famous examples that have been shown in the machine learning literature, where you can have the famous panda example. You can have an image, and then you pass it through a neural network, and you classify it with a panda with approximately 60% confidence, and then you add some carefully crafted adversarial noise, and you not only misclassify the image, but you're also much more confident in your misclassification. But it's not just artificial attacks to the data that can cause such such fragility. There are also natural attacks. So one of my favorites is, of course, you can change lighting in the same image, and you can misclassify, for example, which way the car should go, or that you can take stop signs, and by adding an artificial attack in this case, you can misclassify it as a speed limit sign. Which means that's will lead to catastrophic consequences going forward. So clearly we need to make machine learning more robust. Another trend is that there has been tremendous success from a very different field, the field of robotics, in the area of SLAM. And SLAM is a technique that allows us to map the world geometrically. And what this means is that it allows us to move around and use feature detectors and as well as sophisticated fusion techniques, which I'll talk a little bit about later, in order to get the geometry of the environment. And what this means is we can go around and we can see which part of the environment is free, which part is not free, and therefore that may allow us to choose paths in an obstacle-free way. Going forward, a trend that we see, and this relates a little bit to something I'll talk about later, is beyond geometry, we need to understand the environment. We need to understand the semantics of the environment in addition to geometry. So this is what we call semantic understanding of the world. And I'll talk a little bit later about something we call Semantic Slam, which is not only understand whether there are obstacles or not in the space of the robot, but also understand what kind of objects there are, classify the objects, perhaps in the future further down, understand relationships between objects, and try to reason both in the mapping, but also later in the planning phase about the semantics of objects. Another trend that I see it has to do is, as we send autonomous system in the wild, in outdoor spaces, is a lot of our assumptions about planning and control are based on the fundamental assumption that the environment is typically known. And this applies, of course, in situations such as industrial settings, manufacturing, warehouses, where you know the geometry. You may not know the situation, but you do know the geometry. However, when you send things out, I think one of the challenges is going to be, how do we think about planning and potentially planning with safety in environments that we don't know, and then reactively and in an online fashion we learn. And then we have to reason in an online fashion about how we perform safe plans, safe tasks, and so forth. So that's another trend going forward. My final trend has to do with architecture. This is the classical and familiar to many of us in the control community, command and control architecture that have led to lower levels of control, higher levels of mission planning, that have led to tremendous successes in the areas of autopilots in aircraft, or if you like, also the DARPA Urban Challenge, where architectures like this were tried and proven to be very robust and safe, and mostly safe, and going forward, of course, there is a disruptive paradigm that's coming from a very different community where we sort of let go of modularity and we go directly from sensors to actuators, ignoring models and just trying to figure out what is the best way to think about end-to-end architecture, whether it's in a deep reinforcement learning architecture. And this is, a disruptive paradigm. And it's something that I think the control community needs to think about if there's something for us as a community to say here, whether it is on the safety side or whether it is of how to build such architecture for command and control. I put a question mark because this is sort of a very controversial architecture, but I do think it's something that the control community should be thinking about how to think about these sensor to action maps, especially for unknown dynamics as well as unknown environments. So with that context, I'd like to propose my vision. My vision is not that one architecture will dominate over another, but rather I think that safe autonomy, especially in unknown environments, will require the composition, the rigorous, reliable, safe, robust composition, which will include elements of deep learning, perception, mapping, planning, and control in a feedback loop, which is the title of the talk. The architecture, there's many challenges that our group is working on here in this space. I'm not going to elaborate through all, and this is not an exhaustive list. There are numerous other challenges that the community is currently working on, but the challenges we are working on have to do with safe autonomy, planning in unknown environments, making machine learning and deep learning in particular more robust, as well as learning to act and learning to control. Okay, so I'll touch upon some of these things, but not all of them in this talk. And there's many more that the community at large is working on. So the architecture that I will propose then, and will also use as an outline for my talk today, is going to be the following. So we will use deep learning for the perceptual component, which is where it has shown tremendous success, taking images in and getting some kind of object classification and out. And then that's going to go to some mapping layer, which is going to be integrating over time such semantic observations in order to create rich semantic and geometric environmental maps. And these maps would then go to a planning and control layer, which would then generate controls, plans that will go to our autonomous system. In this case, it will be a legged robot, but this architecture could apply to other such systems, such as the UAV. And then we go around and in this way. So we will clearly have a deep learning layer and going in this loop, and we'll also have this mapping layer. Of course, one can envision other architectures where you replace all of this by one big neural network. That is sort of one of these disruptive architectures, as well as, of course, more traditional, if you like, architectures where, this is replaced not by a deep network, but some other, sensor Kalman filter algorithm of some time ago. So the outline of my talk then is going to be starting with this architecture as the outline. I'm going to talk a little bit, or most of the time, I'm going to talk a little bit about how to think about the deep learning assurance and robustness, particularly for this module. Then the output of the deep learning is going to go to something that we call Semantic Slam. So I'm going to talk a little bit about how we build maps and semantic maps, and then how we take semantic maps into our planning and control layer in order to create paths for robots in unknown environments. Okay, so this is sort of the outline of the talk, and the key sort of the philosophical point here is that there are, we will embrace, we are not going to assume that every component works perfectly. We're not going to assume that deep network works perfectly. We're going to assume that it's going to have some error, and we're going to be mitigating that uncertainty at the layer upstream. And that we're not going to assume also perfect maps, and we're going to then sort of try to mitigate that kind of uncertainty at the control layer or the planning layer, and then go around. So I think the challenge, of course, then here is to embrace the new forms of uncertainty, precisely because we are using deep learning in such the feedback loop. So the three parts of my talks are going to have to, first I'm going to talk about robust deep learning and give you a little bit of an overview of some of the work that we have done in our group with Mahir Fazliap, Jacob Seidman, Manfred Morari, of course, and as well as Alex Roby and Hamed Hassani and others. And then we're going to go to the other part. So let's start a little bit first to talk about robust deep learning. Okay, so we're going to focus here. So as I said earlier, the challenge here is to think about the fragility of deep networks and whether it is an adversary attacking your data, or whether it is nature attacking your data in order for you to misclassify things and therefore lead to either wrong classifications or further down wrong decisions, which can be unsafe. Okay, so this limits to some extent, we need to get the detections much higher in order to be able to get these things to really work reliably in safety critical systems. So the way I'm going to start approaching the problem of fragility is to, we're going to be thinking about feed-forward neural networks here. So I'm going to be thinking about something that is sort of a linear layer, nonlinear activation functions, linear layer, nonlinear activation functions. The data that comes in is an image. It could be a stop sign, for example. It is evaluated through the neural network, and at the end of the neural network, we get some semantic classification that this was a stop sign. Okay, so this is sort of a binary or a discrete variable that says this was a stop sign. Of course, as I said before, one of the challenges is that this is very fragile, meaning that if I add a little bit of noise to the input and I push it through the same neural network, then I get a very different semantic classification. It's no longer stop at the intersection, but rather you can go through at the speed limit of 40. So the question is, how do we analyze the sensitivity of this neural network to perturbations in the input, which is very much, something that a control person should be thinking about. So more mathematically, the way we're going to model the neural network is that we have an input x0 of a particular dimension. The nonlinear activation functions phi, the classical ones go to sigmoidal ones, but we can also take, use, tan H. Of course, the more famous one that is widely used is the so-called ReLU function, or the rectilinear function, which is a piecewise linear function here. So we can use any of those activation functions here. And then, you can interpret, I'm going to be more specific about this later, this as an initial condition, and this is what happens after you go through the neural network after a linear and a nonlinear layer. So this is the linear part, and then you go through the activation function, and then at time 1, you get what this is, and then you keep doing this, and you do this for L layers. So we go deep, we assume that we have L layers, and you can view essentially this neural network as this discrete time system with L time steps, okay? Where we have a linear part and a nonlinear part. Okay, that's essentially it. So now, how do we think about fragility of deep networks? And these are two paradigms. There are many more, but these are two that I think we can discuss here. The first one is, how do I train the neural network in order to be more robust to perturbations? So the classical approach, or the standard approach, one of the most well-known approaches here, is to do so-called adversarial training, or which essentially says if I have data which belongs in two different classes, then what happens is that if I perturb the data a little bit, and then I'm going to cross the classifying hyperplane to the other side, and therefore I'm going to misclassify this data point if I add a little bit of noise here. And in fact, this is how you design the attacks. So rather than doing this, what you do is you do so-called robust or adversarial training, which is you train a classifier so that it classifies the data, even if it is perturbed by some amount close to the data point. And this is sort of the game theoretic, the robust optimization objective that you have to minimize as a training loss when you do the training, where you allow the data to be perturbed by some delta up to some upper bound, and then you train the weights of the neural network in order to be robust to these perturbations. I'm not going to talk at this talk about adversarial training. I have a totally different talk specifically focusing about this, which I'm happy to talk about after the talk. The other approach, which happens after you have trained the neural network. So this is post-training. So you have trained the neural network, somebody gives you essentially the trained network, and then you want to verify or certify whether this neural network is robust to perturbations to the data. So in this case, somebody gives you the neural network. It is, you know all the weights and everything. You are given a data point or a database, and you perturb the data around this point. You push it through, and you would like to see where all the perturbed data land on the output, and whether they, for example, they all land on the same side of the classifying hyperplane. And this is the problem of verifying, given an input set, pushing it through the neural network and verifying where it lands on the output set and whether it belongs in some safe set or whether it belongs on the same side of some classification boundary. So this is an area that there has been a lot of work as well. It's an area that has attracted the attention of both the formal methods community, as well as the control community, as well as the optimization community. In particular, I would classify these approaches in two main categories. The first category of approaches is what I would call exact methods. The exact methods essentially focus on ReLU activation functions because they're piecewise linear, and they break the piecewise nonlinearity by one binary variable that allows you to switch between one or the other. And that leads to a mixed integer linear optimization problem that can verify for neural networks with ReLU nonlinearities. And this can, given a polytopic input, can exactly compute the output because by posing it as a mixed integer linear program. There is a similar approach coming from the computer-aided verification community using so-called satisfiability modular theory approaches, but they're very much similar. For example, the tool Reduplex that is coming out of Stanford would be sort of the first work that that sort of launched a lot of this thinking. The advantage of these approaches is that they are exact. They compute exactly the reachable set. This disadvantage is they focus on ReLU, which is fine for some, but it also are not very scalable, especially as the input set grows, usually. The alternative approach, which is I'm also going to be advocating in our approach, is to let go of exactness, pay a little bit of a price, but push scalability. And the way you do that is by essentially thinking not about MILP type characterizations of this problem, but rather thinking about either linear characterizations or convex characterizations of this problem. And I'm going to be talking a little bit about that. Our approach would fall in this category. So our approach starts by reinterpreting deep networks as dynamical, and if you can also reinterpret them as control systems. So as I was mentioning before, you can start with your system, which can have an initial condition or an initial set. And you can think about this as the initial condition going through a linear system. And here I will show the interpretation of it as a linear system plus a nonlinear feedback. So you have the initial condition going through the linear layer, which is this part, and then it goes to the nonlinear feedback once, and then it comes back, and then it becomes x1, and then it goes again through the linear system, but the weights here may be different from the weights there, which means that your linear system is time varying. Okay, so here time here is the same as layers in the deep network. And then you keep doing this for L layers. Okay, so this is essentially what it is. So first layer, first nonlinearity, second layer, second nonlinearity, and you do this for L layers. Okay, so essentially then reachability or properties of this deep neural network could be interpreted as properties of this linear time varying system with nonlinear feedback. And this it goes a little bit deeper. Even if you have problems of robust training here, they can be interpreted as problems of robust optimal control here, which is something that was known back in the 80s. It was, it has been forgotten, and it actually has come back in the machine learning community this time, discovering robust optimal control for robust training purposes. And if you're interested in that connection, I would encourage you to take a look at this paper that was presented last week at L4DC. So, therefore, now in our particular case, we're interested in sensitivity of deep learning, which means that we have to take now linear a data point here, add some noise, and what we would like to see is how this initial condition without the noise and with the noise, progress through this dynamical system. And then, hopefully, we can see whether this initial condition lands in the right classification zone where we classify this as a stop sign. But, we can see whether this goes outside that classification region, in which case we can say whether this is a misclassification or not. So the point here is that sensitivity of deep networks can be reinterpreted as sensitivity of control systems. And we as a community are very good at computing sensitivities and analyzing sensitivities of systems where we have some kind of uncertainty at the input or at other parts of the system. So this is an opportunity for our community, in my view, to contribute towards this major problem of robustness in deep learning. So now what can we say as a community, or at least what did we say in our group? So the way we are, how do we analyze systems that have linear time varying nonlinear systems with a nonlinearity in the feedback loop? So what we do is effectively get a convex over approximation of the nonlinearity. Okay, this is essentially what we're going to do. We're not going to touch we're not going to change the linear layers. We are fine with linear time varying systems. We don't touch those. We can analyze those well. But the nonlinearity, if we want to do it in a scalable way, then what we're going to do is the input-output behavior of this nonlinearity is going to get abstracted by this quadratic constraint, which will be an over approximation of the input-output relation of the output here. And I'll tell you a little bit how we do it. But this is the key idea. The key idea is that this is going to be replaced by something like this. And then this is, of course, something that goes back to, classical results in robust control, or more recent results in quadratic and integral quadratic constraints, and convex characterizations of them. So essentially, we're going to be paying a price because this is going to be an over approximation. So we're going to be getting something that this system is going to be a superset of the behaviors of this system. So, and what we're going to be doing with that is that if we can show properties, for example, safety of this system or input-output properties of this system, then that by construction will also satisfy here. But if we're not able to prove something here, then it could be that our over approximation is too coarse, and that is fine. Okay, so now our approach is going to, when we look back at the nonlinearities, we don't have arbitrary nonlinearities. We have to take advantage of the specific structure of the nonlinearities used in deep networks. And this is now the current zoo of activation functions. that are being used. Of course, going back to the classic sigmoid, to the more recent ReLU, but then of course there's leaky ReLU, and there's a whole bunch of other things. So our framework applies to all of these. It's not specific to any of them. And the way it does it is by exploiting the particular structure of the nonlinearity of these functions. And what is that particular structure? So in a lot of the robust nonlinear control, we tend to say, well, if a nonlinearity is sector bounded, meaning that it stays within a certain cone, then we can abstract it out. But a lot of these functions here are not just sector bounded between A and B. So it's not that they're just living in this pink zone between AX and BX. They're actually slope restricted, which means that its derivative is also sector bounded. Okay, and the mathematical way of characterizing that is essentially this. So, if x1 and x2 are 2 points, and you look at the images of the nonlinearity, then yes, this is sort of the surrogate for the derivative, and it's between alpha and beta. And this is one way that you can quadratically abstract this out by some quadratic constraint. Okay, so the question then is, how do we do this for ReLU? How do we do this for other nonlinear activation functions? I'm just going to show you for ReLU. So for ReLU, which is the most widely used, this is the definition of the ReLU. And you can decompose the ReLU as these three sets, where this set is convex. This set is also convex, which means I can multiply this inequality by a positive number. I preserve the inequality. I multiply this by a positive number. I preserve the inequality. And if this is unfortunately the one that is not convex, but it is an equality, so I can multiply this with any number, and I will preserve the equality, but essentially this is the part that I will have to convexify. And this is essentially what this is doing. So the ReLU, the input-output, the relationship between x and y in the ReLU function is captured by this quadratic constraint between x and y, okay, where lambda, nu, and eta are parameters, and I can turn those parameters in order to you have a tighter approximation of the ReLU function. And to some extent, these are decision variables in order for me to get the best possible over approximation of the ReLU function and later of the neural network. Okay, this is how you do it. You can do it for other activation functions as well. So the big picture here is that we start with an input with the original neural network. I'm going to show this for one layer, but you can do this for many layers. It's the same thing. And and as I said, this is our original neural network. We don't touch the linear layers. We keep them as is. But the input-output relationship of the non-linear layer, we are going to abstract it out by this quadratic constraint. Okay, and we'll have many quadratic constraints for every nonlinear activation layer. Okay, okay. So essentially, if we want to verify then properties of this neural network, safety properties, robustness properties, assurance properties, then we can do it. Since the input-output behavior is strictly contained in the input-output behavior of this quadratically constrained linear network, then essentially then proving something here is equivalent to proving something here. Of course, we may fail to prove something because there could be a gap between these two models, but it's a sound abstraction, meaning that we can verify it. Of course, the advantage here is that this is now convex, and therefore we can use semi-definite programming to scale this up. And the kind of properties that we are interested in proving or testing here have to do with safety, input-output safety, which we'll talk a little bit about, local robustness, more global robustness, which is related to the Lipschitz constant that I'm going to talk about, but also other things such as detection confidence, closed loop stability, invertibility of a neural network, and many other properties. Okay, so if we want to prove such properties here, we can try to do it here, but pay a little bit of a price. Okay, and this will be more scalable. Okay, so I'm going to show it for one property. I don't have time for more. So I'm going to show it for how to compute the global Lipschitz constant of a neural network. Assume that this is a function, the linear network is captured by a function f, and you're given, it's a global, we don't care a particular point, but we would like to compute the Lipschitz constant of the neural network, which of course should satisfy the classical definition. The Lipschitz constant is very important for a variety of reasons. Of course, it's important from a robustness point of view, meaning that if I'm at a particular point and I perturb by data by epsilon, like I perturb the images by a little bit, then, and I push it through, I have a sort of a quick estimate of how far away the output is, and therefore I can see whether I'm, for example, classified on the right side or whether I stay within a certain safe envelope on the output side. But it's also important if you want to be thinking about, for example, small gain type theorems, if you want to have a neural network with a control system in a closed loop. So it will allow you to such kind of thinking. It's also being used as a regularizer in robust training that I mentioned earlier. And the Lipschitz constant is also useful in proving theorems about generalizability of machine learning and deep learning in particular. So there's many reasons why the Lipschitz constant is a good thing to have if we could only compute it. Okay? And what we're proposing here is a way of computing it in an accurate and scalable way. Okay, and to some extent, the philosophy is going to be very similar to what I was saying before. So we have the linear part and the nonlinear activation function. Now the Lipschitz constant is something closer to an incremental stability type condition, in the sense that nearby initial conditions should lead to nearby outputs. And what you get then is an incrementally constrained abstraction of that. So rather than looking at just X and Y, we're looking at discrepancies between the input and the output. So it's a slight modification. But again, we abstract the nonlinear activation function with something which is a quadratic over approximation. And then if we compute the Lipschitz constant of this neural network, we get an upper bound of the Lipschitz constant of the true deep network. Okay, and here Q is going to be a parameter which we will choose in order to get the tightest possible upper bound. Okay, and this is essentially what it's saying. Since Q is a parameter here, we can pick the Q in a way that sort of gets the tightest possible upper bound, and whatever this semi-definite program gives us is going to be, by construction, guaranteed to be an upper bound of the true Lipschitz constant of the neural network. Okay, and this is nothing more than a theorem version of the previous slide for a single layer. The approach applies to many layers as well. So if you have a neural network with a which with one layer could be written like this, then a STB characterization of Lipschitz constants could be is essentially this, and you can look at the paper for more details. But effectively, any row that satisfies this semi-definite program is, by construction, going to be the square root of rho is going to be a Lipschitz constant of this one layer neural network, and then what you're trying to do is figure out the tightest, the smallest row, such makes this semi-definite program feasible, leading to the tightest upper bound for the Lipschitz constant. So we have a piece of code for this, which we compared it with some of the very limited approaches out there for computing Lipschitz constants. There has been a few more since the paper, and this essentially shows that compared to some of the other approaches, and as well as some trivial upper bounds you can get by multiplying, for example, the layers, the weights of the layers of the neural network, we get the most accurate Lipschitz constants in the literature. It is easy to scale by not being very accurate, and but this showed that we could get the most accurate Lipschitz constants for deep neural networks. And this tells you a little bit of how much we can scale. So I should say that for MILP-based approaches, which compute things exact not necessarily for Lipschitz constant for other tasks. The scalability boundary is usually in the orders of hundreds of neurons, 300, 500, maybe 800. But here, our approach using semi-definite programming by exploiting all the properties of the deep neural network has allowed us to go to, we have a variety of flavors of the algorithm. For example, here we have a network that has 500 layers and 100 neurons per layer. So you're looking at something like 50,000 neurons, 500 layers deep. And you can compute that on a laptop in a few minutes. Of course, you can boost this by going to many GPUs or other high power machinery. But I should say the following, that the scalability of our approach is clearly within what the neural networks that we see in areas such as deep reinforcement learning. But it's very far away or from the scale of neural networks that we see now in computer vision. So we still have a road to go, lots of interesting things, and at least one of the interesting things is to push the scalability of the proposed approach. Other things one can do beyond Lipschitz is, if you have a distribution on the input, you can push it through, and you'd like to compute some confidence interval on the output. You'd like to know, for example, that if this is a stop sign and there's some noise in the image, what is the probability that your detection is the right semantics, is above a particular threshold? Again, same kind of a trick. You over approximate the neural network, and you now compute a lower bound to the probability of correct detection. And this is something actually I'm going to be using for the rest of the talk as an assumption. This is the kind of assurance that the rest of the talk will need. I need to know when I see an object and I classify an object, how confident am I about my, my detection? And this is something that is going to be important later. More recently, we were able to analyze systems where we have a deep neural network in composition with some kind of a linear system. And you would like to analyze not the safety of the neural network in isolation, but rather you want to analyze rather the safety of the robot not hitting a particular obstacle. So in this case, you have a neural network, which you can abstract again, as we said before. And then you compose it with, say, a linear system in a feedback composition. And now you want to analyze not properties here, but properties there about whether, for example, X will be greater than 5, or whether I will hit a particular obstacle at some distance. Okay, and this is something that we have, we have actually two approaches. One is using the approach that I mentioned today. Another approach, which is very different in nature, you can find at HSCC 2019. About using more verification-based ideas. So this concludes a little bit the first part of my talk. And now I want to switch gears and assume that the deep network is going to give us some confidence. Our analysis is going to give us some confidence that I've detected something with some confidence, and my previous approaches may help there. But now we want to take these active observations, continuous observations, and now build maps of the world. Okay, and this is sort of the work that I'm going to be describing. So now when we look at the mapping literature and looking a little bit more in the robotics world, what are some of the accomplishments there? So the big accomplishment is SLAM is a technology. Okay, so we, as I said earlier, we can learn the geometry of the space, and we can plan collision-free paths as we learn an environment. However, precisely because deep learning is allowing us now to detect objects and now reason about the semantics of an environment, which is something that regular SLAM cannot do, that presents really an opportunity to do something beyond geometric SLAM and to really think about semantic SLAM. Okay, this is something that we have been working on. So I want to talk a little bit about our work on how do we take now the output of the neural network and now create semantic maps, okay, maps that have to do with it. So we're going to assume that now we abstract out the deep neural network as something that says that we are in some environment and we have a detector for chairs and doors and things like that. And what we would like to do, we will assume from our neural network is that we have, a neural network will say, well, I just saw a chair. That's the class of the object. I am at least 0.8 to 80% confident that it was a chair, but I may make a mistake. And this is either the location or the bearing that I saw it, okay? And this is the kind of things we will expect the deep network to feed us into the sort of our mapping box. Okay, so now what are some of the things that can go wrong in the mapping layer? So first of all, the deep network will be making mistakes. We're not going to be assuming that it's always right, is always correct. Also, when you go from the geometric to the semantic world, the number of semantic observations may change. Sometimes I may see one human on the street. Sometimes I may see two humans on the street. Sometimes I may see nothing. So the number of observations is also random by itself. It may be low or high, but it's random. And then the other thing, which is well known in the robotics community, is the problem of data association, which means that, well, I just saw a chair and two doors, and I have a map. Which chair does this observation correspond to in my map? And which map object should I update? And you have a combinatorial problem here of observations to objects in your map as far as updating your map as you get more and more semantic observations. Okay, so this is something that we'll be addressing. So the way we address this problem is by something we call Semantic Slam. And a Semantic Slam essentially is something that will also do traditional SLAM, but that's really not the innovation here, but rather it will take also semantic observations on the input. This is the output of the neural network will come here and will be generating both sensor states. In this case, it would be localization, where is the robot, but also a map of objects in the environment. Okay, and the data association is going to be built in here. Okay, so the inputs to our approach will be the standard SLAM things, which I'm not going to talk about. So you get an image, you do some feature detectors, and this is what you would do in standard SLAM or geometric SLAM, nothing to do. You will also you could also have an IMU as an input here. Of course, we can also run this in a purely semantically driven mode where there's no Y and no I at all, and it's just semantics. So these are two inputs. Now, the new input here is the output of the neural network. So in our particular case, we're going to have a neural network that is provided to us by our friends in computer vision at the GRASP Lab, and they do something more than just detection. They do something that is known as semantic key points, where they take an image like this and they will tell us this is a car, and these are some interesting semantic features to track off. A car has wheels and some body elements, and this helps a little bit. This is the way they do their detection. And now on the output, and I'm going to present this sort of as a what are we expecting to get, is this is the input as we get, and we detect continuously object. This is a chair and so forth. And what you get is now a semantic map of the objects that you see. And sometimes you may make mistakes. That's why you see sometimes the objects turning red. And then the green curve tells you the localization, or where you are relative to these objects, or if you're anchored, the global localization in this map. Okay, so this is essentially the output. You get the green curve, which is where are you in this world, and a map of objects. In this case, I'll talk about static objects. Dynamic objects is an interesting direction going forward. Now, the way we do this, this would be the ideal formulation of this problem, which is to figure out the best possible localization and landmarks or semantic observations, and the best possible Data association that, that the new data explains, the way people approach this, not in the semantic world, because there's not that many approaches in the semantic space, but even in the geometric space, is to do some form of a coordinate descent, which is given the data that we have, let's pick the most likely data association. So I see a chair, it's most likely from this position in the map. And then I make a commitment to that assignment. And then given that, I figure out my location and I update the whole map. Okay, and this, of course, you can make mistakes in the original data association, and that has usually responds to very bad maps, especially when you have to deal with loop closure. So the way we have addressed this is by not making a hard assignment on the data association, but rather to make a soft assignment for all possible data associations. So we have all possible graph matchings, and then we put a distribution over all possible. So it's more likely that it came from this map or that map or that chair on the map. And then what we do is we compute the expectation over the over the whole set, the probabilistic distribution over data associations. So this is a very interesting object because it's an expectation over the set of all possible graph matchings from observations to map and semantic objects. This is an interesting mathematical object to study. And the way we have, the question is how do you compute it? And we compute it in an expectation maximization way. But the interesting thing is that the expectation step, which is the part that computes the distribution over all possible graph matchings, essentially is computed using the so-called permanent of a matrix. The permanent of a matrix is a combinatorial version of the determinant of a matrix, which is notoriously hard. But in this particular case, it is okay to do so because A, the dimensions of our matrices are small because these are semantic objects. It depends on the density of semantic objects in your vicinity. And also there are reasonably good approximation algorithms should you need to go to higher scale or higher density of semantic objects. And then once you figure the distribution over the graph matching, then you can compute the localization and other things using more standard SLAM techniques. So the novelty technically here is about figuring out the distribution over all possible probabilistic data associations by computing the matrix permanent of this matrix, which is an interesting thing. So now how does this work? All right, so I should say that this is now code that over the past 2 years we have tuned. It now runs on NVIDIA Xavier. It is something that can run at a rate of 4 to 5 hertz as of now on a robot. Okay, so this allows us now to do semantic mapping also in real time so that we can do online planning and replanning. Okay, and now how does it work? Let's look first at the problem of semantic localization. In this case, the map is known a priori. There's no mapping to be done. This is the famous Kitty data set in Karlsruhe, so the map is known. We know the locations of cars as well as windows. And as we drive around, our detector detects the cars and the windows and uses those in order to localize the car in Karlsruhe in a totally GPS-denied environment. And this is exactly what so you can see here that by detecting, it's vision-based localization, if you like, by detecting all these objects, then it localizes itself in the city. Okay, so there's no mapping here. It's just given the semantic observations, we localize ourselves. The dual problem is you know where you are, but you don't know where the objects are, so you map the world, and this is the problem of semantic mapping. So you have a robot going around. This is on our 4th floor of our building. And it's trying to figure out, make a map of doors. And you can see doors are particularly hard because, because they bring up this problem of data association. If you see a door, is it this door? Is it that door? Is it that door? Okay, so, and then it goes, floor below and makes semantic maps of the world. Okay. So when you put the two things together, then you have semantic Slam, which is You start with absolutely no map. You build a map, and as you build a map, you localize yourself, and as you localize yourself, you update the map, and so forth. Okay, so this is putting everything together, both localization as well as mapping in a totally unknown environment, no GPS, no nothing. Okay, and now how does this work? And let's see how does this work. Again, in Karlsruhe, you can see this is one of the hardest data sets in the Kitty data set, where it goes around, you can detect, it thinks, red means that it's so-so car, and then it's more confident that it's a car, and then it starts building the map. And then, you can also start seeing a little bit, you'll see the loop closure as it goes back to the place that it has seen. And in loop closure, one of the challenges is this a new object, or is it an object that I've seen before? And that allows you to sort of close the loop. And this is where a lot of the traditional SLAM has had a problem, because it was very local. This is a little bit more of a global approach to creating maps. Okay, so this is how we create maps of the world. Okay, so I've talked a little bit about the first part, and I've talked a little bit about the second part. So now we get these maps of the world, and now we have to plan in them and act in them. And this is the last part I'm going to talk about. So, and this is joint work with, some of the work of a group of Dan Kodicek, Vijay Kumar, and my postdoc, Yanis Kantaros, Matthew Malencia, and others. Okay, so as I said earlier, the challenge here is a lot of the work in planning has been in the past as far as planning in known environments. And I think one of the challenges going forward is we're going to be planning now in these new maps, in these maps that deep networks are going to be offering us and generating for us. And I think that is something that's the new form of uncertainty we need to embrace, and then prove properties and guarantees about safety, and do so in an online fashion as we update maps. Okay, so what are the maps out there? This is an area that I think is going to grow in importance. It's already growing in importance in the robotics community, but there's at least two types of maps, and there's many more that I can think of. So, for example, the classic maps you see coming out of the geometric SLAM is occupancy grid maps. So either there's something there or there isn't. And as you go around and you make a measurement, you figure that out and you keep updating the maps. And that's what occupancy grid maps are. And then if you want to enrich these maps with semantics, then you get into something like I was talking about, which is semantic maps, and then you can have fusions of the two, or you can have other types of maps. But these are the new spaces that we're going to have to now design trajectories or even design controllers in order to navigate safely in these new spaces. So the challenge here is, how do we plan in these new representations of the world? Okay, so going back to our architecture, to essentially all of this, the deep network, the mapping technology, from the perspective of the planning and the control layer, is abstracted by some form of a map that can be static, can be dynamic, can be updated online. And then we have some kind of a safety specification. It could be as simple as go from here to there while avoiding obstacles, or it could be something more elaborate, such as do some kind of a temporal logic specification. We have now the robot dynamics, and the robot may also have a lot of sensing capabilities by which it can either understand the state of its own dynamics, or understand or reduce the uncertainty of the environment. Okay, and then the question is, given the safety specification, the dynamics, the sensing, and the uncertain map, figure out inputs, figure out control inputs, figure out trajectory paths. That's so that the robot or the autonomous system meets the specification. But because there is uncertainty, and this uncertainty very likely will be probabilistic, the way we're going to be looking at this is to maximize the probability of satisfying the specification given a map. And then we'll do this in a reactive way, that as the map updates, we can do this fast enough and then replan. Or if you have the dynamics of the map, which is an interesting direction to pursue, then you can bring that into your planning methodology. Okay, either or. Okay, in this case, I'm going to talk about online reactive, but I can see in the future that other approach as well. Okay, so this is the problem. Okay, and now how do we solve this particular problem of given a safety spec, which could be just go from point A to point B, or a temporal logic formula, given a map, figure out inputs to this robot in order to maximize some satisfiability condition or meeting the specification. Okay, so you can pose it as a problem that can be viewed as a stochastic optimal control problem of this form with the two additional two enhancements. First, we need to have maps, and how do we Bayesianly update the map? Okay, and then, or of course, the map could be also static, in which case it only changes by our sensing. But also we have the safety specification, which could be as simple as stay in this box, or it could be more elaborate, like as a temporal logic form. Okay, so these are very hard problems to solve. Okay, we'll be doing them in a finite horizon forward setting. And the way we have done this recently is by using a sampling-based approach. Okay, and the idea here is that this in sampling-based approaches, you start a particular state and you explore the space until you meet some path that is feasible. And then if you sample enough asymptotically optimal. But in this case, we also have uncertainty about the world. So I think here, what we did in this RSS paper last year was not only to sample the physical dimension of where should the robot go, but also to sample the information space. So for example, which motions will lead to uncertainty reduction. And then you can also sample the specification space if you have more elaborate specifications. So this was sort of the innovation we brought. And then you can still have the classical guarantees that sampling-based approaches would have, which would be that first, that it's probabilistically complete and asymptotically optimal, even though I should say that in a lot of the sampling-based approaches, picking the right sampling function and how you explore the space is very critical in getting things to work practically, despite the theoretical guarantees. Okay, so now how does this work? This approach works, and you can, this is something that was presented last 2 weeks at ICRA, which is doing some kind of safe planning, but in unknown occupancy grids. There's no semantics here. This is just about, we have in this case, a more elaborate temporal logic specification. And then we don't know anything about the space. We have some LiDAR, and we build these maps. And as we build the map, we're trying to meet the specification. And things work, in very, very fast, enough that you can even update the environment and even put adversarially some obstacles, and you will still meet the specification. Okay, so now, of course, when you add semantics, this is sort of our vision where we'd like to go. Okay, so this is in a MATLAB setting. It's not in an experiment yet, but this is where we would like to go. So we'd like to have 20 robots meeting a specification that in language would be expressed like this, where some robots go in a totally unknown space. They are all equipped with LiDAR as well as a camera. They'd like to visit some landmarks. They have no idea who is who or where they are. They would like to, and there's also some actors they need to avoid. Like in this case, it's actor 9, but of course 9 could be somewhere else. And then they have to do all these things in a particular sequence. They are sharing a map in this particular case. That's not necessary. But as they, go through the mission, they start, going, in a sequential way, the way the temporal logic dictates, and they do this. And then once the mission is completely finished and they have served all the locations they wanted to serve, they have to get out of the building. But of course, they don't know where the exit is either. So once one figures it out, they have some uncertainty about where it may be. And then once that is reduced enough, then everybody else will follow and exit the building that way. Okay, so this was this is in MATLAB. Red means that we have detected that there's the LiDAR detected that there's something there. And then the cameras detect the landmarks. Okay, so this is to some extent a multi-robot mission in a totally unknown environment, but in MATLAB. You know, more recently, we're able to go from MATLAB to Gazebo, which is the next step, and the next step will be real experiments. So here, this is a Gazebo environment where we have 20 robots, 20 UAVs in this particular case. In this case, we know the geometry, we don't know the semantics, and we're trying to figure out 16 landmarks. There's uncertainty about the landmarks. The landmarks are the red ones. And then as we fly around, we share the map, we share the map, and then we coordinate using the planning approach that I mentioned. Okay, so this happened before COVID, and hopefully we're going to go to experiments once facilities open and we can fly missions like this. So now, all of these things have led to some algorithms that is available to all of you. You can go to GitHub and you can download libstp, which computes Lipschitz constants for neural networks, or deepstp, which computes input-output safety of neural networks. This will be soon on GitHub, our Semantic Slam approach, which is on provisional patent, but also now runs on NVIDIA Xavier, Jetson Xavier. And then here, there's you can download VeriSig on GitHub, as well as soon you'll be able to download the safe planning approach that I presented. Now, all the components sounded fine. Now, the question is, does it work when you put it all together? And of course, one can think about the theory of composition for putting everything together from a cyber-physical systems point of view. But what we were able to do recently over the past 6 months is actually put everything together on a robot and see how it works. So here we were able to integrate all the code, and these are all different parts of what I was presenting today in architecture that runs now on a Ghost Spirit robot. We also here, we not only have the neural network for detection, as well as semantic mapping, as well as the reactive planner, but we also have a second neural network that detects humans. So we can also detect humans in the environment while also detecting other obstacles. So we can do a little bit richer missions. So let's see, does this work when we put it all together? And this is joint work with a group of Kostas Danielidis on the vision side and Dan Kodicek on the legged robotics side. And here you can see what the deep network sees. Here you can see the classical SAM, the feature detection. And here you can see the semantic map as it's being built. The mission here is to track the human in an environment that they don't know. The detector class, it knows that there are chairs in the environment, has no idea where they are, if they are in chairs. And then it just tracks the human, and you can see the semantic map as it's being built, and you can see the human. Sometimes the human disappears, and then exactly the same code, same architecture. We don't have to retrain anything. We just take it to a totally different environment, and it works robustly. So it's still indoors, and it works. And again, same mission, which is follow the human, and in a corridor now, and again, some random obstacles thrown, and it works absolutely fine. Okay, and you'll see this, accelerated going around. So I guess the point here is that the neural network didn't have to be trained for new environment or different lighting or any, new ground conditions or anything like that. You just take the same code and you transition it, and you have some assurance that things will work well. And since things worked well, indoors, eventually we decided to go also outdoors, which is very different, conditions for perception and very different conditions for legged locomotion as well. Again, same task, same, everything worked very well, very robust. And the closed loop with the deep learning and the control and everything was very robust and with safety. So with that, I'd like to conclude my talk. I would like to say that essentially what I was talking about, that this is really a story about embracing new forms of robustness that comes from deep networks and mapping, and understanding them, quantifying them, mitigating them, and then maybe reducing the impact they have at the layer above, and then thinking about them in a closed loop setting. So going forward, there are lots and lots of interesting problems. So I think there's a tremendous opportunity to think about how can robust control and control theory in general contribute towards the paradigm of robust learning and how to make learning more robust. Based on the approach that I presented, one can think about how to scale semi-definite programming while exploiting the structure of deep networks. One can think about safety and stability of deep reinforcement learning. But an area that I'm particularly very excited about has less to do with verifying neural networks, but actually about training neural networks. And this is a new paradigm that we call model-based robust deep learning, where we are trying to make deep learning robust, not so much to adversarial perturbations, but more to natural variations in the data. For example, when you go from day to night, or when you go from sunny day to rainy day, and you'd like to be, one perception to be robust to such very natural phenomena. In addition, as I said, there's deep connections between robust optimal control as well as robust training, which is another direction to pursue. In the semantic slam space, I think one area that I would like to pursue is how to do semantic slam in a distributed way with a swarm and distributed maps, as well as how to do this to understand behaviors in more dynamic and perhaps adversarial settings. So I think getting more into dynamic maps is, I think, is a great direction for the whole community. And then on the safe planning and control side, I think the trading off exploration from a reducing uncertainty while also exploiting in a safe way to say cross an intersection, and managing that tension between uncertainty reduction and exploitation from a safety point of view is going to be something that is going to be interesting. And one area by which we sort of balance that out that we are pursuing recently has to do with the mathematical notion of risk and how to do risk-aware planning specifically when we think about perceptual uncertainty, and how do we quantify that uncertainty, and how do we think about risk-aware paths given what do we mean by risk, and what notion of risk may make sense. And then if you're interested from a more logic point of view or a task point of view, we're also thinking about risk-aware semantics of temporal logics. So with that, I'd like to conclude my talk by thanking the organizers as well as my group for their being a fantastic group to work with. Thank you.